Okay, hello everyone, and thank you for joining the webinar. My name is Mark Bollinger, and I'm with the Lawrence Berkeley National Laboratory. I'm joined today by my colleagues, Dev Milstein, who is also with Berkeley Lab, as well as Sophia Hamilton, who is a PhD student at UC Berkeley and who did a lot of the heavy lifting on this project. Sophia, you want to just introduce yourself quickly?
Hello, this is Sophia. Like Mark said, I'm a PhD student in civil and environmental engineering at Berkeley, and I was working up at LBL on this project with my other co-authors here. So excited to be here presenting with you guys.
Okay, great. Thanks, Sophia. So the way it will work today is that Dev is going to present pretty much all of the material, and Sophia and I will monitor any questions that come up while Dev is presenting, and then we'll also help with the Q&A portion of the webinar a bit later on. Before I hand it over to Dev, though, there are just a few quick things to note. First, as you probably know by now, Zoom has both a chat and a Q&A function. We would ask that you only use the chat for administrative purposes, for example, to let us know if you're having technical difficulties. Otherwise, if you have a question that is content related, please use the Q&A button, as that will allow us to more easily track questions as they come in and also to distinguish new questions from those that have already been answered. So please use the Q&A function. The webinar is being recorded and will be posted on our website along with a copy of the slide deck in the near future. And then finally, I just want to note that this work was funded by the U.S. Department of Energy's Wind Energy Technologies Office, and we do appreciate their support. So with all of that out of the way, let me now hand it over to Dev.
Okay, hello everyone. Welcome and thanks for joining. As Mark mentioned, my name's Dev Milstein. I'm with the lab. And so the title of this talk today is How Does Wind Project Performance Change with Age in the United States? And so let's jump in. Okay, so I want to talk about three main themes today. The first theme is really an overview of the key results, including context and implications, and some of the key methods that we used. Second, I'll talk a little bit in more detail about some of the methods, and also I'll talk about some of uncertainties and sensitivities of our results. And finally, I'll talk about future research directions on this topic. So all the material we're talking about today is published in an article in Joule. This is an open access article, so anyone can download it and read it. The link is here, and you can also look at our website. Electricity Markets and Policy is the name of our group. It's at Berkeley Labs or LBL, and you can see this is the landing page for this project at our website. I'll go ahead and paste those links into the chat right now in case you want to copy and paste them. Okay. So why is it important? Why do we need to know the rate at which performance changes with age for wind plants? And it's important that this piece of information is important because it helps define how much expected generation you would see for a plant over its lifetime. So not just the total generation over the lifetime, but when that generation occurs. And that profile of expected generation over a plant's lifetime is an important input into these two applications here, levelized cost of energy estimates, so that's per kilowatt of hour you generate over the life of a project, what's its cost. And also it's important for a long-term electric system model. So if you're modeling out the power system for a couple decades and you're looking at how it will evolve over time, it's important to know how much generation from different wind projects you will see over the course of their lifetime. And each of those topics, each of those applications are used for lots of other topics as well. So we could keep this tree growing with more branches beyond these two we're showing here. Levelized cost of energy, for example, is important when looking at the financial viability of a plant, or it's also important in energy modeling as well. And the long-term electric system models can be used to look at different policy decisions and regulatory decisions. So this analysis could be an input into many different applications within the field. And so to date, at least in the United States, there hasn't been a comprehensive research study on how the wind fleet as a whole has performed with age. And there's been quite a lot of research on individual component reliability, but that does not provide sort of generalizable insight into a whole plant or fleet. And maybe because of this lack of information to a certain extent, performance changes over time are typically not accounted for in estimates of levelized cost of energy or in some of these forward-looking electric system models. So we're trying to fill this gap with this study. I do want to note that this is not just a wind issue. All machinery declines in performance over time, especially rotating machinery. So all other power generation technology also has similar issues. What's unique about this work is not that that it's new for the wind industry in the United States. So our study looked at the performance across 917 plants. Here's a map of those plants. They're all located in the contiguous United States. The orange dots are newer plants, and the pink dots are older plants. For this work, we set a dividing line at 2008. So plants that were built in 2008 or later, we called new, and older plants built before 2008, we called old. So we'll keep that grouping throughout. And we did two main analyses on this data set. So the first analysis, we wanted to understand the fleet-wide performance sort of on average across the fleet, the rate of performance decline with age. And for that analysis, we used this fixed effects regression technique, which it's a linear regression, but it has extra turns in it to isolate the impact of age and separate out the varying impact at the plant level. And so that allows us to get one sort of fleet level impact of age on performance. Now, the second type of analysis we did was we wanted to see why some plants have more performance decline with age and some plants have less performance decline with age. And to understand the differences between plants, we used this multivariable regression, and we explored how plant characteristics were correlated with the rate of performance decline. So two types of analyses, one a fleet average analysis, and the second looking at differences between plants. Okay, a couple items about the methods. We needed to adjust performance over time for weather variation and also for curtailment. So for weather variation, we don't want to have, so some years maybe have higher average wind speeds than other years, and we don't want to mistake a trend in the weather variation for a trend in the performance. We're looking for how the plant performed given its wind speeds. And so to do that, we used modeled wind speeds at the hub height of each project. Specifically, we used a reanalysis model called ERA5. Another thing we had to take account for was curtailment. And so curtailment occurs in the wind industry when there's too much generation at a particular moment and location relative to the demand for it. And so you could imagine if there's a large wind farm behind or that must transport its electricity across a transmission line, and at a certain hour there's so much wind generation that there's a limit, it reaches the limit of what the transmission can carry to the load center. And so then the plants behind that transmission line will have to curtail a little bit or a lot, depending on the hour. And so we didn't want to also incorporate trends in curtailment over time as performance trends, since those are sort of exogenous to each of the wind plants. And so we had to estimate curtailment for each plant. We do have sort of regional values reported for the amount of curtailment. So this was the process of taking the regional values and distributing them basically to the plants within the region. We used local pricing patterns and the status of the plant, whether the plant was receiving production tax credits, for example, in order to distribute that curtailment from the regional level down to the plant level. So those were two important adjustments we made to the records of generation we had to remove issues related to weather variation and issues related to curtailment.
Hey, Dev.
Yes.
We had a question come in that I thought might be worth answering right now. The question is whether you only looked at or really only used ERA 5 data for all wind farms, or did you try other reanalysis data and ERA 5 ended up being the best fit?
Yeah, that's a great question. We did try looking at MERA 2 reanalysis data, but we actually downscaled the MERA 2 reanalysis data to using this wind toolkit that's developed out of NREL. It's a much higher resolution data set. And in our initial tests, the ERA 5 data seemed to perform better in terms of the interannual variability. And so we went with the ERA 5 data.
Okay, great. And we've had another question come in just about the specific definition of curtailment. Are you only looking at grid curtailments or also capacity deratings, or both?
I guess I'll hold off on that curtailment, that question for now. I would say our source of data for curtailment is what is reported at the ISO level. And maybe I can come back to the to that answer that offline.
Yep, and so I think that's primarily just going to be economic curtailment. That's pretty much what the ISOs report. Okay. And then just one other question, and then I'll let you move on. Someone asked what is the source of the plant-specific production data?
Great. So the EIA, the Energy Information Administration, reports monthly generation from all wind plants, and that was our source. Great questions. And I'll continue on, but in general, I am happy to answer these questions throughout, especially if it helps clarifying specific issues like this. Okay, so that was the sort of top-level overview of the methods, and now we'll jump into the results. So this is the main figure from the paper, and I'll spend a little time talking about all the features we found that were interesting in this. And I will talk about why we think we see those features, but I'll do that after I explain all the features themselves. So just hold off for a few slides, and then I'll explain what our hypotheses are for the behavior that we see. So these figures show this normalized capacity factor index. You can think of that as just sort of percent or a fraction of performance compared to the year 2 or an early year performance in the wind farm, in wind plant. And so we see that, so one thing we see right away is that the first year of these wind plants have lower performance. And that's often due to a phased installation of a plant or teething issues, testing things out, things that happen at the very beginning of the plant life. And after that first year, then plants reach sort of full production level starting in the second year. In the newer plants, it looks like maybe those teething issues last a little bit longer than the year, since we see some increase in performance up to year 3 beyond year 2. But most of that occurs during the first year. In terms of the performance decline over time, we see a difference between new plants and old plants. So old plants are on the right and new plants on the left here. And you can see that the rate of performance decline is a little bit higher for old plants compared to new plants during the first decade of life for each set. This performance decline rate of about 0.2% for new plants, that's a very small amount of performance decline. That's really low. Old plants have about 0.5% loss per year. And so that's about 3 times the size of the decline we see for new plants. Once plants go beyond 10 years of age, we see this interesting feature where the performance drops rather suddenly after 10 years. And so that drop is about 4% for that period right after year 10. And we can see performance drops, has a little rebound, and then continues with a little bit of a steeper decline for the last few years of our oldest plants in our sample. And so those are the main features I wanted to tell you about today. There's 4 of them here. There's this very low level of degradation for the newer plants during the first 10 years. There's a slightly higher level of performance degradation for the first 10 years of older plants. There's this drop after 10 years that we see, and then finally continued degradation in the end years of our sample. And then just for some context here, the overall, for the oldest plants in our sample, they're still operating at 87% of their year 2 performance at the end of the time period. Okay, so let's understand the context for these results. Let's compare them to wind fleets in other countries. So Staffel and Green in 2014 did a study of the wind fleet in the UK, and they found a performance decline of about 1.6% per year. And so that's much higher than the performance decline we saw here, even for our oldest set of turbines. Their sample looked at turbines from 2002 through 2012. And the Staffel and Green figure here is on the top left. We modeled our fixed effects methods after their techniques, and so they have a very similar figure to us. One thing that's interesting is that they have this linear decline throughout the time period, whereas we found that discontinuity at 10 years, and then a steeper slope for the later time period. Another study out of Germany, that's this figure on the bottom left here. This study found a performance decline of about 0.6% per year. So this is more similar to the results we found, especially for our older set of plants. Their figure is interesting because they didn't present exactly the performance decline here. What they're presenting is total generation from the wind fleet, which would be this gray area, and then the additional generation that could have occurred had losses been reduced, and they split up losses into these different categories. This sort of medium orange color is the age loss. So that gives you a sense for the scale of the issue here. If you have an expanding fleet like we do in the US or like they did in Germany during this time period, you can see that the loss from performance decline is not negligible, but it's also not terribly large. That the medium orange color there is not too large, or it's pretty small compared to the total gray. Finally, there's another study in Sweden that also found similar performance decline to the study out of Germany, which is 0.6% per year. So overall, if I just go backwards for a second here, the level of decline that we saw, even for the oldest plants, is on the lower end of the range. If you look across, not the last few years, but across the full 17 years, it's on the lower end of the range that we see from the other wind fleets. So in general, that's good news. That's relatively mild performance for the US wind fleet. And then the newer plants show really small levels of performance decline over their first decade of life. So let's talk about why we see those features. And we sort of break up this why question into two categories. So one explanation is tax credits, and a second explanation is technology. So let's talk about how we think tax credits are influencing these patterns. So after 10 years of operation, the wind plants receive a production tax credit for the first 10 years of their life. Most wind plants do, not every single one. And after the 10-year window, then they stop receiving those tax credits. They still receive payment for the energy they produce based on whatever contracts they've negotiated. So this production tax credit provides an extra incentive for maintaining your plant at its peak capacity so that you can maximize your revenue during that time. After that window closes, your operating profit drops, and so the hypothesis is that so too does the rigor of your maintenance protocols. And so this is a little bit consistent with results we've heard from a survey of wind professionals as well. A second hypothesis is that some project or turbine component lifetimes are about roughly 10 years. And so maybe after 10 years, there's sort of this natural period where you have to have your plants have a little bit of downtime while you refurbish these components, and then they go back up and have slightly better performance. This could explain why years 11 and 12, if I go back here, why years 11 and 12 have slightly lower performance than year 13, but then as the plants continue to age, the overall decline continues. So that there might be a natural sort of refurbishing of the plant after 10 years or so. And if you combine that with the production tax credit, maybe that sort of natural refurbishing is delayed a little bit until after you stop receiving those tax credits, and then you refurbish the plant to a certain extent. And finally, there's this result, or really the magnitude of the drop after 10 years is sensitive to the plant level curtailment. I'll talk about that sensitivity more later, but for now, just know that that's one of the uncertainties. Not really that the drop exists, just the exact magnitude of the drop. Let's talk about why we think newer plants are performing better than the older plants. So one thing is component reliability. We know a lot of older turbines had faced sort of a higher rate of gearbox issues, for example, and newer turbines are not facing those same issues as often. There's also a possibility that for technical improvement in operation and maintenance maturity. So there's new sensors and controls in newer turbines. There's newer software that can sometimes improve the turbine performance as well with updates to the software. So this may be a reason why the newer plants are doing better. And then finally, there's turbine design itself. Newer turbines are of larger blades relative to capacity. That's this quantity called specific power. And I'll go into details about that in a minute or so. But the actual turbine design itself might be influencing things. And then finally, contracts. have tended to have stricter turbine availability and project performance guarantees. So that may be also encouraging better maintenance protocols. So these findings illustrate that the aging of the plants is not strictly a physical phenomenon. It's managed, and it's a cost and benefit trade-off, how much to spend on maintenance versus the cost and the performance increase.
Hey Deb,
so,
before you move on, we've had a whole bunch of questions come in, a lot of them related to interpretation, so I think you probably knocked a bunch of those off with that last slide there. But there are a few that I thought it might just be worth touching on before you move on. So one of them, someone asked about the confidence bands around the results for the new versus old plants. Did you see tighter confidence bands around either the newer or the older plants, or were they fairly similar? Do you have any recollection of that?
Yeah, the p-values for the slope of the new plants and the old plants were really small, and so they were highly confident about those slopes. Beyond that level of detail, I don't have anything at the moment.
Okay, and then just one more question for now. Someone was asking how you moved from the ERA 5 data to simulated output, specifically whether you had to estimate power curves, or did you just use the monthly average wind speed, or how did that work? So I thought you might just mention, just say a few words about the power curves.
Yeah, so we chose a power curve specific to the dominant technology at each plant, and we then used those power curves with hourly wind speeds from the ERA 5 database, and calculated generation each hour, and then summed that up to monthly and annual totals.
Okay, and the key point being is that we're accounting for turbine design evolution by using updated power curves for each specific plant.
Exactly.
Yeah. Okay. Thanks, Dev. Go ahead and proceed.
Okay, great. Thanks for the question. Now we're going to switch into the second topic here, which is trying to understand why some plants perform better than others. And right, and I should say why some plants have less performance decline with age than others, rather than their overall performance. We're not looking at that. We're just looking at how they change over time. So for this topic, we looked, first of all, we looked at a subset of plants. We only looked at new projects. So those are plants that were built in 2008 or later, and we looked at projects that had at least 5 years of data so that we could get a trend for each of those projects. We picked the new projects because we wanted to find differences that were relative to decisions that are being made now. We weren't as interested in understanding why plants built in the early 2000s, for example, had greater performance decline than plants built in a decade later. So we're more interested in the technology that's in the field now, or that's relatively new and in the field now. So for that reason, we selected only the new projects. For each individual project, we found the rate of its performance and how it changed with age. And then we ran a multivariable regression across all those projects to determine which plant characteristics influenced the rate of performance change with age. And the plant characteristics that I'm talking about are listed here. I won't go into every single one of them, but they ranged from characteristics like project size and turbine-specific power, so how large the blades were relative to its capacity, or terrain roughness for each project. We also looked at things like who the owner of the project was and characteristics of that owner. And I'm going to highlight 8 of the 13 characteristics here to talk more about. So these are the 8 I wanted to talk about. Obviously, everyone might be interested in a slightly different set. So first of all, project nameplate capacity, and these are our prior hypotheses. So this is what we thought we'd find before we ran the multivariate regression. So we thought that larger projects would have some economies of scale, allowing for increased operation and maintenance, maybe increased monitoring or on-site personnel, and that could reduce degradation rates. Similarly, we thought projects with larger owners, or perhaps owners with dedicated wind knowledge, may be able to establish more cost-effective operation and maintenance programs to reduce degradation. Turbine-specific power, I'll go into this in detail in a minute, but this is related to the turbine blade size. And we thought that these larger plants would have lower degradation. And average wind speed, we thought, but so this is interesting because a number of these variables actually could have both positive and negative effects on degradation over time, and wind speed's one of these. Higher wind speed might mean more time spent at rated power, which would allow for lower degradation, but it also might increase turbulence, which might increase stress on the plant and cause more degradation. Turbine OEM, this is original equipment manufacturer, and obviously differences in turbines design and component reliability could lead to differing performance between the different manufacturers. Terrain roughness, we thought that increased terrain roughness might increase turbulence or increase other types of stressful weather conditions that could cause greater mechanical stress on the turbine. And then finally, similar to the reasons we thought we saw that 10-year drop in performance, we thought that plants that received the ongoing production tax credit versus plants that received a grant at the beginning of their project, but not the ongoing production tax credit, would have a higher incentive for aggressive operation and maintenance, and therefore lower degradation. So this was a subset of all the characteristics we looked at, and then when we ran the multivariate regression, we found that only a small number of these actually had significant correlations with degradation rates. So I highlighted in orange here the ones that we found significant relationships with. So one of them is turbine-specific power, which I'll get into in a minute. Second, we did find that the average wind speed, the higher the wind speed, the lower the degradation rate. And we also found that flatter terrain reduced the degradation rate, or more rough terrain increased the rate of degradation. So let me talk about specific power here for a minute. This is one of the major trends we've seen in wind technology over the last couple of decades has been an increase in size of the turbines, but specifically an increase in the blade size versus the increase in other attributes. So here on the left, we see the turbine with sort of average characteristics from 2009, and on the right, we see a turbine with characteristics from 2018. And we can see the 2018 turbine's much bigger. It's only a little bit taller, but the blade size has increased. And what that does is really increase the swept area of the plant. And that's an important metric. So the swept area here, the circle is growing faster than the capacity of the plant is itself. And so what that means is if you have a larger area that you're sweeping with the wind, but say you have the same turbine capacity, then you can imagine you have the same resistance in the turbine, but a larger blade, which you can use to then spin that turbine, and that allows you to get to full rated capacity at a lower wind speed because you're harvesting the energy from a larger area. And that is the main thing that's driving this relationship to performance decline. So the specific power itself is just the capacity of a plant divided by the swept area, the blue circle here. And so as you get really big swept areas, you get lower specific power. And let's look at how that affects the power curves. Here we can see the power curve as shown here is the sort of fraction of full power compared to the wind speed. So on the x-axis here, we have wind speed increasing, and for newer turbines, we get to full power at a little bit less than 10 meters per second, but on the older turbines, 2009 turbines, you have to get up to about 12 meters per second. And so until you reach full power. And the key thing is that at full power, you minimize your losses from, or some of the performance losses you'd expect over time. So if you imagine your blade edge eroding because of, or over time, and your blade is a little bit less efficient, but if you're already at full power, then you can, if you're above this point here on the power curve, then you have a little bit, you're already shedding some of the potential energy you could be harvesting because you're at your limits of how fast your turbine can spin. And so you're already shedding a little bit of energy, and if you have some efficiency loss, then instead of, you can just shed a little bit less energy, but stay at full power. And so these newer turbines with really large blades and low specific power operate at rated full power about twice as much as the 2009 turbine, and that allows them to dampen the effects of aerodynamic losses like erosion over time. So that's the connection between the technology change, moving to really large turbines, and reduced performance decline over time. Okay, so let's just review this, the results from looking at different plant characteristics. The main results we found were that lower specific power, the really large blade turbines, had less degradation over time, and we think that's related to them spending more time at their full rated power, reducing the impacts of aerodynamic losses and other related losses. Terrain roughness, we found that turbines in rougher terrain had increased degradation over time, and we think this is related to weather-related stress. Mean wind speed, this was significant only when we removed outliers from the sample, but we did see that these higher wind speeds reduced degradation over time, and we think that's also related to just spending more time at rated power. Okay, so
hey,
maybe
Deb,
there's some questions.
Yeah, I'm just going to jump in with one or two questions here. One is about wake effects. Did you consider wake effects in the plant characteristics?
Yeah, so we considered, well, because we didn't consider wake effects within the plant. What we were interested in wake effects from other plants. If a bunch of new plants are built upwind of a project, it might conceivably, there might be intra-farm wake loss. And so we did have a proxy for that, which we did not find to be significant.
Okay, and then just one more. Someone was asking if the fact that the PTC versus the 1603 grant does not correlate with changes in performance, does that argue against the hypothesis that the year 11 drop is related to the end of the PTC window?
Yeah, that's a great question. I don't know if it argues against that, but it's certainly something to think about. This was all within the newer plants, and so we'll have to see how newer plants respond after 10 years, and we don't have a long enough time sample yet for that to see if they will show the same decline in performance after 10 years that the older plants did. I would say that we did find the sign of the coefficient there did indicate that the PTC plants had less performance decline than the grant plants, but it wasn't statistically significant. So it could just be that we lack the statistical power to really pull that out.
Okay, yeah, and just to reiterate, the 1603 grant was available to plants that came online between 2009 and 2012. So as Dev mentioned, they fall only within the newer cohort of plants. And so it's a little early or it complicates the comparison because of that. All right, Dev, thanks. Proceed.
Okay. All right, I just want to point out, a couple things that our results are most sensitive to and where the most uncertainty in our results are, and then talk about future research directions. So one thing that is challenging is the lack of publicly available plant level data, and this adds some uncertainty to our results. Now, we do have publicly available generation data for each plant, but what we don't have is curtailment data for each plant. I talked about this a little early, and we also discussed it in a question as well. But our process of estimating curtailment was important to getting the results that we found. And what's particularly sensitive to that process is the size of the 10-year decline in performance. And I would say if we don't account for differences in curtailment patterns based on the plant's status related to the production tax credit, so that means just distributing curtailment more evenly across plants, it actually increases the size of that performance drop after 10 years quite substantially. Now, so that doesn't show that the performance drop should be larger. It just shows that magnitude, the specific magnitude of the performance drop, is most sensitive to us not having reported curtailment data. A second issue is the weather correction. We're using model data to correct for the weather, and that's because we don't have measured wind speeds at wind plants at hub height. The model data adds some uncertainty to our fleet-wide results, and if we completely remove the weather normalization from the analysis, then the difference between the rate of performance decline in new plants and older plants goes away. Now, again, that's not the correct way to do it. The correct way is to weather normalize the plants, but what that shows is that the difference in rates of decline between newer and older plants is somewhat sensitive to the weather normalization. So those are sort of two key uncertainties that hopefully we can resolve over the next few years in this analysis. So future research questions, this already come up, like what will happen to the newer plants in the next few years? Unfortunately, we have to wait a few years to find the answer to this, but it will be very interesting to see if this performance decline occurs after 10 years for these newer set of plants, and also to see how their performance decline changes into later years in project life for the newer set of plants. Will they continue to perform better than the older set of plants over their second decade, for example? That'll be an interesting question. And then it will also be interesting to further diagnose factors of performance decline. So why do some plants have greater performance decline than others? And some of the questions we could try to refine are related to terrain roughness, for example. So this is really supposed to be a proxy for turbulence or other extreme weather conditions. And maybe there's a way to refine that proxy so we can look at whatever actually is underlying the performance decline that we see associated with rough terrain. And then it would also be interesting to improve our proxies for interplant wake effects. So we could look at if construction of new plants nearby is affecting existing plants. And then finally, we have a great set of research now across multiple different countries. It could be really interesting to harmonize those data sets and have a really big sample then to look at these plant characteristics and their effect on performance decline, and also to really understand the differences between the different fleets in these countries. Okay, so just to sum up, and then I can take a couple questions or additional questions. So first, this is the first comprehensive study of how performance changes with age in US wind plants. New plants, we found have very little degradation over their first decade. Older plants have some degradation, but overall, the degradation in especially new plants, but even in old plants, is on the lower side compared to fleets in other regions. Performance declines to 87% in year 17. So overall, that's less than 1% decline per year. Although we did find in the later years that the decline was slightly greater for the later years in that set of plants. Plants with low specific power, flat terrain, and high average wind speed tended to have lower levels of performance decline with age. Those were the most significant results we found from looking at the plant level characteristics. So finally, while plant aging is inevitable, we've shown that it's a managed process, and it's sensitive to operation and maintenance protocols, even to policy incentives and to contracting. And it's ultimately a cost-benefit trade-off that decisions that plant operators are making. And I guess we could try and take some lessons for ourselves from this, that we should all take care of ourselves and make sure our operation and maintenance protocols are good, and go for extra runs. And so take care of yourselves, and thank you for listening. If you have questions, you can email me here. And this research is open access again. Here are the links, and we can go to questions now.
Great, thanks, Dev. We have a lot of great questions coming in.
Okay.
So we'll try to get through them in the next 10 minutes. The first one involves the possible impact of software upgrades to change the rated power of the turbine, and also the use of aftermarket components to kind of upgrade the turbine above and beyond, or to keep it in better shape than it may have come from the OEM originally. How did we account for that? Do you want to speak to that?
Yeah, so theoretically, a project could actually have increasing performance over time. For example, I think there were some GE turbines that had software upgrades that increased their capacity beyond what they originally were rated at. And there are items such that you can attach to the blade edges that reduce the blade erosion or remove blade erosion that's already occurred. So those are a couple examples of those types of technologies. The way we would have let those be part of the performance description. So plants that did see improvements due to those technologies would have had less performance decline, or possibly even performance increase over time. So that would have been incorporated into all our statistics, and we did not specifically include, we didn't know which plants had those changes exactly, so we couldn't put those as a separate variable in our multivariable analysis, but in general, it would have been included in the underlying performance. Great.
So another question, we obviously accounted for variations in wind speed, but did we also consider environmental impacts such as rain or icing rates on losses?
Yeah, early on in the research, we tried to look at that, and we could not look at that satisfactorily. Maybe Sophia, you might want to say a couple words about that.
Yeah, I remember I couldn't find really good data on like precipitation and stuff like that at all the wind farms, so we didn't end up including it in the end. But yeah.
Yeah, that's definitely something we're interested in. So perhaps we can add that on to our future research analysis.
Okay. Someone else was asking kind of exactly how year one is defined, just noting that when plants come online, over a period of several months, and the first turbine might be installed in September and the last one in November or December. And so in that case, does the first year one, start in September or in December?
Yeah, the first year starts at whatever is the first month the wind plant starts selling generation into the grid. So it would be the first month that it reports generation to the EIA. And so the first year would be that month plus, or the 12 months starting then.
Okay. Someone else asked about, going forward in the future, wind plants might start to provide a greater amount of grid services or ancillary services, and can we speculate at all about how that might impact performance?
Yeah, that's interesting. So if it really depends, I think, a lot on how, if a wind plant wants to provide sort of head space so it can ramp up if it's needed. That might, if a wind plant is sort of purposely keeping its generation a little bit lower because it's selling the possibility it could ramp up at a particular moment, then that could reduce its observed performance. It would maybe, or presumably it would overall increase its revenue, but reduce the performance, or at least the appearance of performance, just by looking at total generation. I don't think that's an issue yet, but that is something we'll have to be careful of in the future.
Okay. I think you kind of touched on this, but can you say a little bit more maybe about why the difference between the U.S. and some of the European experience here?
Yeah, so there are not the same production tax credits available in Europe that there are in the U.S. for 10 years. And so that's one reason why we think this 10-year change is related to the production tax credit. We saw these linear declines in the European countries and this sort of discontinuity after 10 years in the U.S. Another difference was that our time period of analysis went longer than a lot of the previous studies, so that we were able to get a better idea if there was a difference between sort of the newer plants and the older plants. Some of the other studies saw hints of differences between plant vintage, but weren't able to develop a full relationship there.
Okay, and perhaps related to that, someone asked whether we looked at contract structures such as length of warranty and different ownership structures, and if so, what impact that might have.
Yeah, we did not have that data to analyze that. I would presume that would have a certain amount of impact on the results, but we don't have the data to differentiate between plants.
Right. Okay, someone kind of brought up repowering here. Given the disparity in performance degradation between old and new plants, would we expect repowering to occur earlier than originally estimated? And if so, any estimates at where the break-even point is? Does performance have to decline to 50% before it makes sense to repower? Do you have any thoughts on that, Dev?
Yeah, so we're just beginning to see the first sort of wave of repowering. So we don't have too much data from the field yet on this. But there's a lot of things that might influence repowering decisions. One thing being whether the repowering allows a plant to be treated as new in terms of the production tax credit, so they get a new 10-year phase when they can get the production tax credits. That would probably be a stronger influence than whether the performance decline is 10% or 15%. from the beginning of the plant operation. In terms of break-even points, that I don't have any information about. Mark, do you have additional thoughts on the repowering?
No, I was just going to agree with you that I think, the PTC is going to be the primary driver there. So, if there's an opportunity to capture another 10 years worth of PTCs, even if your plant is performing relatively well still, it might still make sense, economic sense to go ahead and repower that plant. Someone else asked about, did we look at projects that are under contract via a PPA versus projects that are either post-PPA or have some other sort of merchant arrangement?
Yeah, we did include an explicit merchant or not merchant plant characteristic variable, which was not significant. So we thought maybe PPA plants would have higher incentive to have better maintenance, but we didn't see a statistically significant result there.
Okay.
One other thought about repowering is there's also issues related to value of the energy you can create. And so this trend towards higher or lower specific power, these larger turbines, also allows generation across more hours of the year and can help increase the average value that you receive for your wind turbine. So that might be another influence into why you might choose to repower that's sort of separate from the performance decline.
Okay. Someone else asked about the old versus new question. How statistically significant is that difference between the two, and is it possible that the year 10 drop might be either partially or fully explained by some sort of statistical fluke, or possibly by some factor other than age?
We did check statistical significance comparing all these things, and they are significantly different from each other. So I don't think it's the statistics that's obscuring things here. There certainly could be an explanation that we are not aware of. Maybe something related to warranties, or I don't know. I would just be speculating at this point. We haven't thought of another explanation that seems as reasonable as the production tax credit explanation for the year 10 drop. And we also think the difference between new and old plants is pretty robust, although I did point out that uncertainty related to the weather normalization.
Okay, and then maybe this will be our final question, given that we're out of time. Someone is asking you to kind of prognosticate a little bit here, and is wondering whether you predict that degradation for newer plants that came online after 2008 will be similar to, or less than, or greater than what we've seen for the older plants in their later years. Okay,
sure. This is just a total prediction, though, without any particular data backing it up. But I would guess that the newer plants will continue to perform better than the older plants over their second decade of life. And the reason I would guess this is because we saw the link to technology change through improved lower specific power, the larger blades, and then also the improved sensors and maintenance protocols. So that's why I think they'll continue to perform better over their second second decade of life compared to the older plants.
Okay, great. There were a few more questions that we did not have time to get to, but we have record of those, and if you've left your name and email, we will try to get back to you and answer those after the webinar. So Dev, any final words?
Oh, thanks everyone for joining. I hope it was interesting and entertaining, and I hope to talk to you all again soon.
Great. Thanks everyone. Bye-bye.